All right, the last estimator is called the unbiased estimator. When we try to deal with the population total, most of the time that we would rely on the cluster average or like the per capita average and multiply to the total number of population in the entire population, like the capital M. But if that capital M is not available, then we cannot simply use that to multiply to using the ratio estimator to find the total. But we can form another estimator of the population total that does not depend on M. That's called the quantity YT bar. YT bar is indeed the cluster total, YI, and then we add them up together for N of the cluster that we sample and take an average of it. Okay, so YT total is an unbiased cluster average. Then using the cluster average, simply we multiply this YT bar to capital N, then we can obtain the total. So at the end of the day, this unbiased estimator could be used for our population total estimation. And the estimated variance would be the final population correction factor times ST square over N, and ST square is simply the cluster total difference to the cluster average taking square over N minus 1. Okay, so when we are up to this point that we have talked about 4 estimator under the cluster sampling. First is the ratio estimator, which is the per capita average. So very much like the means of means. And the ratio estimation sometimes is biased. Then we can say that if the cluster size are all equal, we could have an equal size cluster estimator. And lastly, the 2 estimator, the probability proportional to size and the unbiased estimator, are a additional variation of the estimator. One is that when we choose the sample from the population, we choose it proportional to the cluster size. And lastly, the unbiased estimator would be a simple average of all of the cluster total, and that would be the unbiased estimator to help us to find the population total. Okay, so with this estimator for total tau under ratio estimation, and for the equal size estimator, we can use a capital M multiply to our Y bar under ratio estimator, the double bar, because this indicates the per capita average, right? So the per capita average is obtained from ratio estimator. If we multiply that with the capital M, that is the total number of populations, total number of elements in the population, so we can find the total. So estimated variance of tau is M squared multiplied to the final population correction factor times SR squared over M. Secondly, probability proportional to size. Now we have the Y bar PPS. This is obtained from the cluster average. So if that's the case, when we need to estimate the tau total would equals to the cluster average multiplied the total number of clusters in the population. And then the estimated variance formula is simply S squared multiplied to the estimated variance of Y bar PPS. The unbiased estimator, when M is not available, then we again use the unbiased estimator for the cluster average multiply to the total number of cluster in the population, and we have the estimated variance find it accordingly. Okay, so the remarks are saying, oh, I'm very confused with which estimator that I'm using. We look at the relationship. If YI, or the estimates that we are interested in, is uncorrelated with the cluster size, then we can use the unbiased estimator with the cluster size does not matter at all. Or we can consider when the cluster size is constant, then we can use the unbiased estimator to help us to do the estimation under cluster sampling. If yi is positively correlated with mi, so if yi, the data that we're interested in, goes up together with the size of the cluster, then we can use ratio or the probability proportional to size estimator, because under this two estimator, mi, the size of the cluster, matters. That would add the variance to be calculated for the cluster sampling. So mi, or the size of the cluster, matters under our calculations. Then within the PPS and the ratio estimator, if within cluster variation does not change with the changing of the size of the cluster, then we can use a probability proportional to size. Whereas the within cluster variation does varies, or that increases with the increasing of the size of the cluster, then we need to use the ratio estimator. Okay, so if we look back to our examples 6.6, we can see the size of the cluster that matters. So first of all, we think that the unbiased estimator is not applicable in this example. And then we see that if the cluster size increases, and then the yi does not necessarily increase at the same direction. So if that's the case, they are more or less remain a constant for the variation of the yi within each of the divisions. If that's the case, a probability proportional to size is more applicable than the ratio estimation. Okay? I will give you some additional cases. For example, which estimator is best applied for the following situation? An automobile forms a nice cluster of 4 tires for studies of tires wear and safety. So let's say if I have, I want to sample the cars. Now looking at the tires to see how many of them have already worn and need to be tested for safety. Then each of the car have 4 tires. So for this cluster sampling, we have equal size cluster sampling. Secondly, a circuit board manufacturer for a computer forms a cluster of semiconductors for testing. Under this situation, we find that if we assume that the yi does that the are within clusters, and then we can observe that the variations of the yi, or the failure of the semiconductors, the variation does not change even if the cluster size changes, then a PPS would be more applicable. Lastly, an orange tree forms a cluster of oranges for investigating an insect infestation. If we can see some of the larger trees, they would have more oranges. As a smaller tree, they have smaller number of orange. And likely, the number of the insects infested for the larger trees would be higher. So the variation of yi does vary with the larger tree, or does varies within the smaller trees. So if that's the case, a ratio estimator would be more appropriate. So in other words, for the case of A, we can use a unbiased estimator because mi is constant. For situation of B, I would say the PPS would be more appropriate if we see the within cluster variation does not change. And situation of C, that we say a ratio estimator would be more appropriate because we see a larger variations of the yi with would vary with the cluster size. Okay. So let's go back to the lecture notes that we more or less saying the same thing. And lastly would be on the sample size determination. Under the cluster sampling, we don't put too much emphasis on the cluster of the sample size determinations. There are two factors under the cluster sampling. First is the number of cluster that we are going to sample, and secondly would be what is the relative cluster size. So most of the time that we assume we have no control on the cluster size, so the MI, we cannot choose that. The only thing that we can choose is to choose how many number of clusters to be included in our sample. So under the sample size determination section, we'll probably just look at the determinations of how many cluster we want to sample given a certain bound of error. Okay, so just like how we did in the previous chapters, we want to relate the standard errors multiply to the critical values must be less than equals to the bound of error. So this is to why I should take this out in here. Okay, so if that's the case, again, we simplify that. We find the equation for the number of clusters to be sampled would be greater equals to n SR square over n. B would be the bound of error for the average per capita, which is under the ratio estimation, multiplied to m bar square divided by z square plus SR square. Last examples should be 6.8. Suppose the data in the table represent a preliminary sample of incomes in the city. How large a sample should be taken in order to estimate the average per capita income with the bound of $500? So now we are given the ratio estimation with the bound of error per capita. And then we can use the data from the previous example. We have SR square given, and we can estimate the average cluster size for the population using the average cluster size under our sample using little m bar. And the bound of error is at $500 here, so we substitute in there, and we can find that we should sample at least 167 clusters. Okay, so that's it for cluster sampling. Again, I would say that under cluster sampling chapter, we did not touch too much into the cluster sampling for a further study on the multi-stage cluster sampling. What we just did is to stay with one-stage cluster sampling, and then with the four estimators that we've talked about. Okay, so I hope you find cluster sampling an interesting chapter as well. Okay.